Okay, members, I welcome you back. We have had some good break from when we last talked about chemistry. It's hyperchemist. You can call me Nicholas from Gaza High School. This is my WhatsApp contact. In case something gets wrong as you follow my videos, you can reach out to me and we discuss. So previously in my videos of last year, I recorded about benzene and its derivatives, but I had given you some version of mechanisms, and I want to give you an alternative. So I want us to start the topic together and finish it together. We are going to look at benzene and the basic derivative of benzene that we are going to talk about is methylbenzene or toluene. And this will be done in 3 or 4 videos according to what is available. So benzene and its derivatives. Now, when you talk about benzene, we shall find it as the simplest member of aromatic class of hydrocarbons. We've got hydrocarbons, or the substances which consists of carbon and hydrogen atoms only, but then we've gotten aliphatic hydrocarbons and aromatic hydrocarbons. So benzene is in the class of aromatic hydrocarbons, but it is the simplest member. So I may not write that, but we need to note that it is a colorless liquid and it has got a molecular formula. So here we shall have molecular formula of C6H6. Yeah, it has got molecular formula of C6H6. Now, then when it comes to the structure formula or the structure of benzene, for so many years or over years, benzene was known as a cyclic compound with a 6-membered ring of 6 carbon atoms and 1 hydrogen atom. But the carbon atoms were predicted to have alternating double and single bonds, joining them with a ring. So basically, the structure of benzene initially was C. We had C. You will forgive my pen, but we shall go through together. So these are single bond members. So this is C. This is C. Here we shall have C. Shall have C. And we shall have C and another C. So these are carbons, but then here we have a double bond. We shall also have a double bond here. We shall also have a double bond here. Then on each carbon, we've got hydrogen. We've got hydrogen. We've got hydrogen. We've got hydrogen here. We have hydrogen here. And we have hydrogen here. So this is the structure of benzene. Now, this structure was proposed by the man who was called Kekule in the year where none of us was around, but it is 1865. And this structure can most conveniently be written as, you can conveniently write it as this. Okay, you can write it as that. Now, this Kekule structure was, however, not accepted by some chemists because it would simply imply that benzene undergoes addition reactions like benzene, so rather like alkenes. And some chemists came up with the more suggestions, yeah, and that one may not be our main concern of other structures other scientists are proposed, but we just need to know what it is about now. So basically, we shall note that if the structure was correct, then it would be possible to have some different disubstituted isomers of benzene that can be isolated. However, in no case was more than one isomer of that compound obtained. So Kekule modified this structure, okay? Kekule modified this structure, meaning that this structure we can derive more other resonance forms of this structure. So he proposed that benzene rapidly alternated between different structures. So one can have it drawn as this. You can have it drawn as this. And this one can as well be alternated to this. So it's a matter of alternating the bonds, yeah? So I can have this here, and I can have this here. And you can also alternate it as this. So these all are resonance structures of benzene that were proposed by this man called Kekule. Now, in this, we are going to see why benzene, much as it is having double bonds, why it does not undergo the same reactions the same way other alkenes do. So we need to note the reason as to why benzene does not undergo electrophilic addition like ethene and other compounds containing carbon-carbon double bonds. So we are going to look at the reason why benzene does not undergo electrophilic addition. This is a very common question in organic analysis, why benzene does not undergo electrophilic addition like other compounds having or containing carbon double bond. So we want to see the reason as to why it does not undergo electrophilic addition. As we continue, when we start the chemical properties of benzene, we are going to find out that for benzene, it strictly undergoes electrophilic substitution, whereby an electrophile substitutes the hydrogen in the benzene ring. Okay, but for electrophilic addition, the electrophile or the electron deficient species add across a double bond or across a multiple bond. So the reason as to why benzene does not undergo electrophilic addition is simple. We are going to find out that the pi electrons in benzene are not fixed, because we've seen that they can undergo resonance. Those electrons, the double bond, can undergo resonance, and those bonds are the ones where we have the pi electrons. Okay, so the pi electrons in benzene are not fixed compared to other alkenes, so they are not fixed to any two carbon atoms, but rather are delocalized, over the entire benzene ring, over the entire structure. Okay, making benzene very stable, making benzene very stable and not easily attacked by electrophiles, are not easily attacked by electrophiles. Since they want us to compare with other compounds containing carbon-carbon double bond, so we have to bring in the aspect. So now, what conclusion do we make from here? Since those double bonds are not is attacked by electrophiles, you're going to say that therefore benzene does not undergo electrophilic addition, basically due to resonance stabilization. So the best way I would love you to present this, you can begin with this. You can say, benzene does not undergo electrophilic addition due to resonance stabilization. Then now you tell me, how does it come about? You tell me that the pi electrons in benzene are not fixed to any two carbon atoms, but are delocalized over the entire structure, making benzene very stable and not easily attacked by electrophiles. You are able to get all the marks by writing for us that. Then you compare with other carbon-carbon double bond compounds. So you will say that, however, carbon double bond, carbon-carbon double bond in alkenes and other, in alkenes and maybe other compounds containing multiple bonds has delocalized, has localized pi electrons, hence a center of high electron density, thus readily attacked by electrophiles, So this is what we need to write to be safe. This is what we can easily write to be safe. You talk about in alkenes, the double bond being localized, having localized pi electrons, while in benzene ring, those bonds having localized pi electrons, making it not fixed, meaning those electrons can keep revolving, forming different resonance structures. Another thing that I want you to note from here, I want you to know that benzene only undergoes electrophilic substitution reactions and maybe other reactions, but within the ring, the reaction that takes place within the ring is electrophilic substitution, where an electrophile or electron deficient species replace or substitute the hydrogen atom in the benzene ring. Okay, so you need to get this note before we proceed anywhere else. For now, we shall have to look at the stability of the benzene ring. I'll record that one in my last lesson under benzene. I'll talk about the stability of the benzene ring. But for now, let me first save that. Okay, so let me go to preparation of benzene, or how benzene is prepared, and then we look at different reactions of benzene. Okay, for now, let's first look at preparation of benzene, and maybe after preparation of benzene, that is when I can bring the stability, and then we go to the chemical properties. Because before we look at chemical properties, we need to first check how stable is the benzene ring. And that is why we consider the thermochemical measurements of benzene. Yeah. So now, let's look at preparation or methods of preparing benzene. Yeah. So preparation of benzene. For preparation, for you to prepare benzene, there are some very many methods that you can use, and I'll be giving you a number of alternatives which are best for our synthesis, right? So the first method we can carry out polymerization of ethine. Polymerization of ethine. Now, like last year, 2020, actually named 2020 much as they start in 2021, they examined these students to describe the conversions without using equations, meaning they wanted them to use what? So I want to challenge you members that you must be well equipped with the names of the substances that we shall be using. So for you to prepare benzene by this polymerization of ethine, we heat ethine. So basically, when ethine is heated at a temperature between 60 to 70 degrees Celsius under the pressure of 5 atmospheres in presence of complex organonickel catalyst, we form benzene. And by the equation, we shall have ethine. This one is going to be polymerized in presence of complex organonickel catalyst at a temperature, one can use 60 degrees Celsius, or even if one uses 70, it is okay, but you can put this. This one will automatically be giving you your benzene. So one can draw the one with a ring, or you can draw the one with bonds. But for this one to happen, we need 3 molecules of ethine. Similarly, you can get the same without using complex organonickel. Still, I can carry out polymerization of ethine using iron or copper. So you can as well use I still need 3 molecules of ethine, but I'm going to use different reagents. So I'm going to use copper, and I'm going to do that at 400 to 600 degrees Celsius. So this will still give me benzene. Alternatively, still under polymerization of ethine, I'll use my 3 molecules of ethine, and I will heat this in presence of iron catalyst using the same temperature, 400 to 600 degrees Celsius. Still, this one will give me benzene. So all in all these reactions can give you benzene through polymerization of ethine. That is number 1. Method number 2 that I can use to get benzene, I can decarboxylate benzoic acid. So this method one can call it decarboxylation of benzoic acid. In the near future, we are going to see how is this benzoic acid coming about. How does it come about? So in the carboxylation of benzoic acid, this is where the carboxyl group is removed. And for you to use the carboxyl group, in other words, let me first show you, this is my benzoic acid with the carboxyl group. So for me to decarboxylate or to remove this carboxyl group, I'm going to heat this benzoic acid with the soda lime. It is a very accepted reagent. Soda lime, you just heat. Without heating, you will not get it. So you heat and strictly you get your benzene. There are those people who want to show off that, you know what soda lime is. So if you want to show what soda lime is, but I don't really recommend that, you can still decarboxylate This is my benzoic acid. Now, this soda lime is a mixture of two solid substances. That is solid calcium oxide and solid sodium hydroxide. So you can say CaO, but you must show that it is solid. Then sodium hydroxide, still you must show that it is solid, and then heat. Now, this is risky because you can easily make a mistake by writing. If you write the formulas badly for these substances, then we don't have mercy. So you have to just say soda lime. Or if you're sure that you can write this, you have to put it. Now, basically, this reaction can also be done in 2 steps. You can do this reaction of soda lime in 2 steps. How do you do this in 2 steps? If you want to do this reaction of using soda lime in 2 steps, you can as well get that benzoic acid. After getting this benzoic acid, you react it with the solid sodium hydroxide and heat. This will give you sodium benzoate. First get your sodium benzoate, COONA. Then from sodium benzoate, you add soda lime. In other words, I've first gotten the salt of a carboxylic acid, then now you add soda lime. But why do you break like this? Soda lime and heat. So to avoid all this, just add soda lime and make it a point. So these are so far the 2 methods we have looked at, but we still have more. Still, one can get it. The 3rd method we are going to outline is from phenol. I can get it from phenol. You can get benzene from phenol. Phenol is a derivative of benzene also, though, but if we reduce, actually, you can call it reduction of phenol. If you reduce phenol, reduction of phenol, you reduce phenol. How do you reduce phenol? You get phenol, you heat it with the zinc dust. So if you have phenol, OH, and you just heat it with the zinc dust, heat, automatically, it is going to give you benzene. You heat it with zinc dust, you get benzene. Now, also, now I'm going to give you some other uncommon methods of preparing benzene, and the methods which are not common, I may say, but which can be used to prepare benzene. More methods, we can get it from diazonium chloride, benzene diazonium chloride, or from a diazonium salt. In the near future, we shall be seeing how we form a diazonium salt. But since we've not looked at reactions of benzene, it may be hard for us to form a diazonium salt. So for now, let's see if we have a diazonium salt, can we form benzene? Then we shall pick up from there. So we are going to look at how we get benzene from diazonium salts, okay? So still, by reduction of a diazonium salt can be my 4th method. Reduction of benzene diazonium chloride. So benzene diazonium chloride, how does it go? I will have the benzene diazonium chloride. This is N plus triple bond NCl minus. This is my benzene diazonium chloride. I'm going to reduce this by using hypophosphorus acid hydrolysis. Yeah, so we are going to use hypophosphorus acid solution. Hypophosphorus acid solution, that is H3PO2, because I want it to be a solution, so it is in presence of water. And this one will automatically be giving you benzene. Yeah. Very many more other methods. Very many more other methods. I can get my benzene still from bromobenzene. Can get it from bromobenzene. From bromobenzene. This acid, we've said that it is hypophosphorus acid. Yeah. So we are going now to get it from bromobenzene. Now, for bromobenzene, you can use as very many routes as possible. You can first convert bromobenzene to phenol. You can first convert bromobenzene to phenol. How do we convert bromobenzene to phenol? You can use steam. Yeah, you can use steam, that is gas, in silicon, and you maintain the reaction at 425 degrees Celsius. You have to know the temperature. This automatically will give you phenol, and then you reduce phenol by heating it with the zinc dust. So if you heat phenol with the zinc dust, you're going to form your benzene. That is the first way. Similarly, you can pass it through Fittings reaction. Fittings reaction is where you first form methylbenzene from bromobenzene. If you have your bromobenzene, I'll be having bromobenzene, you can first form methylbenzene by passing this bromobenzene through chloromethane with the sodium in dry ether. The moment you react bromobenzene with chloromethane, sodium, and dry ether, this automatically will be giving you methylbenzene. I told you that we shall look at this derivative of benzene on its own. Then now for this methylbenzene can easily be converted to benzene. How? We react it or we pass it over platinum, heated platinum in presence of hydrogen and aluminium oxide as a catalyst. So we have PT and aluminium oxide, and this reaction is maintained at 600 degrees Celsius. This will still give you this. Why am I giving all this? Because we know that you people read and get different alternatives. So I've decided to give you all the alternatives that maybe you would expect to form. So that is what you have. However, there are some other longer routes. There are some other longer routes that one would take. I'm going to summarize them here. Other laboratory longer routes that one would take to form, other longer routes that one would take to form this benzene. So basically, we are going to look at those methods, other methods, but I'm going to summarize them here. And these methods can be from a diazonium salt. I'm going to give you methods from a diazonium salt that lead to the formation of benzene. I'll be very fast here. If I have my diazonium salt, triple bond, NCl minus, one, I can pass this, I can add acidified water. I told you never begin with water and then you put an acid. If you do that, then my worry will be if you would survive in the lab, beginning with water and then acid. It must be an acid, then water. This one will give you phenol. This one will give you phenol, OH. And then you use your zinc dust. You heat this one with the zinc dust. You can call it zinc solid zinc, and you heat. Automatically, this will give you benzene. Alternatively, if you have this diazonium salt and you add the potassium iodide, and warm. If you add potassium iodide and warm, you'll get iodobenzene. You'll get iodobenzene. Now, from iodobenzene, you can need to take it to phenol, then still it will go to the same thing. How do you take it to phenol? Sorry. You add steam, silicone at 425. You find yourself at phenol, then you add that. Still, you can use other reagents to get other compounds. You can add copper 1 chloride, aqueous copper 1 chloride. When you add aqueous copper 1 chloride, you add also conch, HCl. This would give you, since we added a copper 1 chloride, we shall get chlorobenzene. You add copper 1 chloride aqueous with conch hydrochloric acid, you get chlorobenzene. From chlorobenzene, you add same materials. You add same materials as this. Steam in silicon at 425, you get phenol, you continue. Still, I may not need to get chlorobenzene. I may need bromobenzene. For you to get bromobenzene, now for the case of bromobenzene, add the copper 1 bromide, aqueous copper 1 bromide, aqueous copper 1 bromide, aqueous copper 1 bromide in conch hydrobromic acid. In conch hydrobromic acid. The acid you are adding should be correlating with the compound you're using. So if it is copper 1 bromide, you must use conch hydrobromic acid. If you use conch hydrobromic acid still, add the same reagent, steam and silicon at 425, form phenol, get your answer. Then the final route that I'm going to consider is where you add copper 1 cyanide. You have copper 1 cyanide. You add copper 1 cyanide in presence of potassium cyanide. Yeah. Aqueous. This must be aqueous. You're going, this one you must warm. Actually, for all, even here you will warm. For all these substances, you have to warm. This will give you benzene with a cyanide. Now, for this case, you add the acidified water. This is very common actually. You have acidified water and heat. It will give you a carboxylic acid. Some people, actually, this is the cheapest, amongst the cheapest reactions. So this will give you copper 1, rather will give you a carboxylic acid. Then from this, to get to benzene, of course, you have to decarboxylate by adding soda lime and then heat. You find yourself there. Okay, so the final method is the industrial one, where we compress the petroleum vapor, though it's not examined, but you need to know the science behind. So from petroleum, you can say from petroleum, that is the industrial one. From petroleum, how do we go about it? Petroleum is CH3, CH2, 4, CH3. What we do, we pass petroleum over finely divided platinum, and we maintain the reaction. This is a catalyst. We use platinum as a catalyst. Maintain the reaction at 500 degrees Celsius. And the pressure of 10 to 20 atmospheres. This will give you benzene and hydrogen gas, 4 molecules of hydrogen. So that was it with synthesis. Actually, for your own information or for your own consumption, this synthesis one can also call it reforming. You may be somehow funny sometimes. They ask you to define cracking. They ask you to define reforming. So you should know how we got about that. Okay, now from here, we are going to go to the chemical properties of benzene. And that is where the science is, where we look at the reactions of benzene. Yeah. Everything. So we are going to look at the reactions of benzene. And as I've told you, this is where the science is. I want you to note that, as I told you when I was starting, in the former videos, I was giving some mode of mechanism, and now we are giving some other mode of mechanism. So I want you to understand all so that you always use your best. So, dear children of God, let's look at how benzene reacts. Chemical properties of benzene. Chemical properties of benzene. So in this video, I'm going to include 3 chemical properties, then other chemical properties. I'm going to put them in another video so that it is not too long for us to watch. Or if they can be, but they may not fit in. So I'm going to do only 3 within this, and then or 2, I may do 2 in this, then I do the rest in the other video. So chemical properties of benzene. Now, as I've told you, you must note that benzene, as I told you before, does not undergo addition reactions like other alkenes, but mainly undergoes electrophilic substitution in the ring. So basically, we are going to look at electrophilic substitution. Electrophilic substitution. That substitution takes place in the ring. Substitution. Now, when I talk about electrophilic substitution, the word electrophilic comes from the word electrophile, and electrophile means those species which are electron deficient, meaning that electron deficient species are replacing the hydrogen in the benzene ring. Okay, so the reasons as to why it does not undergo addition, we've already talked about them in my introduction. Okay, now we are going to find out that the pi electrons, basically, when we are carrying out the mechanisms, we're going to find out that the pi electrons serve as the sources of electrons. Okay, the pi electrons, they serve as the source of electrons. Okay, so we are going to look at a number of reactions that benzene undergoes, and those reactions range from nitration, sulfonation, Friedel-Crafts alkylation, Friedel-Crafts acylation, etc., as we are going to be seeing. So the first reaction we are going to look at is nitration. Nitration. Now, dear children of God, when you talk about nitration of benzene, you need to know that we use an equimolar, or we use equimolar quantities of conc sulfuric acid and conc nitric acid. You must use the equimolar. When I say equimolar, it means that if you've used 1 molar sulfuric acid, 1 molar, even nitric acid must be 1 molar, okay? So what you're going to do, we are going to have benzene. You have benzene. Now you are going to add conc nitric acid. We shall add conc nitric acid and conc sulfuric acid, conc nitric acid and conc sulfuric acid at a temperature 55 degrees to 60 degrees Celsius. One can pick 55, it is okay, provided it's the range. So this reaction leads to the formation of what we call nitrobenzene. Nitrobenzene. and water. This mechanism is a bit tricky because some students normally miss some steps in it. Now, this nitrobenzene formed is called, oh, its color, it appears as a pale yellow liquid. Pale yellow liquid. So we want to see under what mechanism, under what routes we form this nitrobenzene. I want you to note that for you to form nitrobenzene, or when we talk about nitration, nitration is facilitated or enhanced by equimolar amounts of conc nitric acid and conc sulfuric acid at either temperature 55 or 60, or if you're not sure, you can use that range. Okay. Now the mechanism. For the case of this mechanism, remember the reaction is electrophilic substitution, meaning that we must generate an electrophile by ourselves. For any reaction of benzene that involves a mechanism, you must generate an electrophile by yourself. Even if it is sulfonation, you must generate an electrophile by yourself. If it is if it is Friedel-Crafts alkylation, for whatever type of reaction, you must generate an electrophile by yourself. How do we generate an electrophile by yourself? Here, you may ask yourself, why is it that I'm forming a nitro compound? Now, what is the essence of sulfuric acid? Sulfuric acid is there to play two roles. The sulfuric acid, concentrated sulfuric acid is there, first of all, to protonate the nitric acid. Okay, it is there to protonate the sulfuric acid. So in other words, the weaker nitric acid will act as a base in a high acidic sulfuric acid, and hence it will accept a proton to form rather from sulfuric acid. So what am I trying to communicate? Sulfuric acid will be used to protonate the nitric acid first. So we shall first form protonated nitric acid. Okay, so what happens is the nitric acid, I'm going to write it in a simpler way for you to understand. So I'm going to say HONO2. That is how I've managed to write my nitric acid. So during protonation, because protonation will involve one proton or one hydrogen getting to this nitric acid, so it means that the hydrogens in sulfuric acid are going to be reduced by one. So I will have the hydrogen sulfate ion, be left with the hydrogen sulfate ion. Oh, sorry, but this is a minus hydrogen sulfate ion. And I will also be left with now a protonated nitric acid. The protonated nitric acid will be now, for protonation here, will be a plus on an O. So I will have O plus. Then I will have the two hydrogens, the one which you're seeing here, and then another one which is from sulfuric acid. Then the rest will remain the same, NO2. Now, this is what we call protonated nitric acid, okay? Protonated nitric acid. So the first role of sulfuric acid, of conc sulfuric acid, is to protonate nitric acid. Then another role of sulfuric acid, I've told you it plays two roles, is to split or to decompose the protonated nitric acid to release a nitrile or a nitronium ion, which we shall be using as our electrophile. So the protonated nitric acid that we have formed will split, is going to split, and on splitting, it is going to release a nitronium ion that we use as our electrophile in attacking. So we shall have that this protonated nitric acid will split to form water. As you can see, here we shall have water, then plus a nitronium ion, NO2 plus. One can call this one nitrile cation. One can call this a nitrile, or one can call it nitronium. We love this nitronium because it is the commonest. So we shall form a nitronium cation. Now, what we shall do These two equations, a student who writes them will get a mark. But a student who has understood the concept, who knows that ideally we shall form a nitronium ion, can generalize these two equations and you write one equation. So one can combine these two equations if they are sure. Here you must be sure because the equation must be balanced. You can write a general equation instead of writing those two. If you write them, you'll get a mark. But even if you write this general equation, you'll get a mark. How does this general equation work? Remember, we are saying that sulfuric acid plays two roles, meaning that for each step, we shall have sulfuric acid, implying that in the general reaction, you write that we have 2 molecules of sulfuric acid. Why am I writing 2 molecules of sulfuric acid? Because sulfuric acid is protonating, that is 1 molecule, and another sulfuric acid is splitting the protonated nitric acid. So there are 2 molecules of sulfuric acid reacting with nitric acid, and this will lead to the formation of the nitronium cation, NO2 plus, because this is what I need majorly, then plus the hydroxonium ion plus, then plus 2 hydrogen sulfate ion. If you're so sure, you can write for me this. This one generalizes and gives you the whole mark. Someone who has spent time and written this, still, you get your 1 mark. Someone who has generalized it, you get 1 mark. Now let's see. After we have generated our electrophile, which is a nitronium ion, my interest is here. So this nitronium ion, I want to see how it reacts with benzene to form nitrobenzene. So what we are going to do, we are going to see how we form nitrobenzene. So what we do, you're drawing your benzene ring. So I told you that there are different resonance structures, but me, I'll be using this through. So we are having our nitronium ion. So we say that the pi electrons serve as the source of electrons, meaning that they will donate electrons to these ones which are in need, because a nitro group is an electrophile, meaning it needs electrons. So what do? We shall momentarily form a nitro group here. But remember, since the electron has been removed here, electrons have been removed, so this is now unstable. When electrons are given away, where they have gone from, we put a positive charge. But what has been attached? What has been attached has been a nitro group. But this nitro group is supposed to replace the hydrogen. So this hydrogen is going to stabilize this bond where you have put a plus, and this will lead to the formation of, after losing this hydrogen, because remember, you said that it's all about substitution of an electrophile to the place where the hydrogen was. So we shall have, after losing the hydrogen, you'll form your nitro group. So this is it. This is it that you can write. And that is it for the first reaction of nitration. You need to note the steps that we have used. 1, first protonate the nitric acid. After protonating, then you split the nitrated nitric acid to give a nitronium ion, which nitronium ion is your electrophile. Then, during the mechanism, I told you that for the case of the starting procedure, you can use any of the 2, the general one or the 2. Then on the mechanism, let that bond first attack that electrophile. That electrophile will be on the benzene ring momentarily, not until this hydrogen stabilizes the ring, and then you form your compound. The second reaction, The second reaction is what you call sulfonation. The second reaction is sulfonation of benzene, sulfonation. Now, when we talk about sulfonation, sulfonation occurs when benzene is gently warmed with fuming sulfuric acid at some temperature and for some time. So basically, we have sulfuric acid here. Rather, we have benzene. I'm going to react it with fuming sulfuric acid. You can use fuming sulfuric acid at a temperature of 35 to 50 degrees Celsius. And this will give you benzene sulfonic acid. Yeah, this will give you benzene sulfonic acid. And water. You get benzene sulfonic acid and water. What does it mean? It means that the sulfonic group, this group, is the one that we shall use during the reaction, okay? Then now, one can be like, now, what if I want to use concentrated sulfuric acid? You can as well use concentrated sulfuric acid, and then you reflux the mixture for about 8 hours. So you can use still benzene. It is the same reaction, but instead of fuming sulfuric acid, I can use conc sulfuric acid. You will say conc sulfuric acid. Here you heat, or even if you say reflux, you get still benzene sulfonic acid and water. You still get benzene sulfonic acid and water. Now, in both cases, you are going to find out that the hydrogen atom in benzene is substituted by the electrophile. So this electrophile now will be the SO3, as we shall see. So let's see how the mechanism goes with this. So the mechanism here will be after we have generated an electrophile. So how do we generate an electrophile? We are going to have the sulfuric acid, whether fuming or conc, splitting. And those must be 2 molecules of sulfuric acid splitting. And this will give you sulfur trioxide, hydroxonium, and hydrogen sulfate. So at this stage, now you bring your benzene. After we have generated this electrophile, now you're going to bring your benzene. So you're going to bring benzene. The structure, I'm sorry, but you modify it well. You modify this well. So we shall have sulfur. You can really put some good strategy on bonding. Sulfur is bonded to 3 oxygen atoms. So what we shall have this coming here on sulfur, and here we shall have this. So this will lead to the formation of benzene ring. Now here, where it has moved from, we shall have a plus. And then here, we shall have SO3. Here, since you create a minus, so here we shall have minus. And then we shall have hydrogen atom. This hydrogen atom that should be displaced is going to stabilize the ring. And on stabilizing the ring, if you lose it, you're going to lose it. And on losing it, you'll form such a compound which is with SO3 minus, but remember our aim is to form benzene sulfonic acid. So for you to form benzene sulfonic acid or to attach a hydrogen, you'll add hydrogen ion. So don't be like now you have removed it and bringing it back. Please. Here we removed it because we are substituting the hydrogen. We don't want the hydrogen on the benzene ring. But this hydrogen that we are adding is the one that is going to make it sulfonic acid. So we are going to have benzene with SO3H. Good. So these are the reactions that involve formation of that involve sulfonation and nitration. Maybe before I end this lesson, let's also look at some other reaction of benzene. Then we are going to come for others which have many mechanisms. We have hydrogenation of benzene, hydrogenation of benzene. So for the case of hydrogenation of benzene, you are going to have benzene okay. For hydrogenation, that is why you have a mixture of hydrogen and benzene vapor. You pass it over nickel catalyst at 150. So we shall have hydrogen gas, nickel catalyst, 150 degrees Celsius, and this will form cyclohexane. This here is cyclohexane. So in other words, hydrogenation distorts the structure of benzene by removing the double bonds, forming cyclohexane. Interesting. So from this, in my second video, I'm going to talk about other reactions which involve tight mechanisms, and these reactions would include Friedel-Crafts alkylation, Friedel-Crafts acylation, etc. But I wanted, before we cross still, I wanted to show you the importance of this, because we are going to find that benzene sulfonic acid is quite much used in synthesis. So we need to know where is it applied. This benzene sulfonic acid that we have gotten here can be used in preparation of phenol, and that is a very common application of benzene sulfonic acid. So we need to see where is it used. Okay, so if you have your benzene sulfonic acid, and you need phenol, you first add aqueous sodium hydroxide. So we shall first add aqueous sodium hydroxide, and on addition of aqueous sodium hydroxide, you're going to form you are going to have in SO3Na. Then now here from this, you add solid sodium hydroxide. At this point, you're going to add solid sodium hydroxide at a temperature of 360 degrees Celsius, and this one will give sodium phenoxide, where you'll have ONA. For us, we don't mind, even if you don't give us the charges, it is okay. Then now, by hydrolyzing this with a dilute acid, which is preferably HCl or sulfuric acid, you're going to get your phenol. So this conversion should be part of you as we move for the future. One may be like, now this sulfonation. Actually, this sulfonation is also a useful process in manufacture of detergents, dyes, and drugs. So we are not doing it for fun or for anything else, but we are doing it for industrial preparation of some substances like detergents, dyes, and drugs, as you will be seeing as your chemistry keep moving from one step to the other. So allow me first call off this lesson, and I prepare ground for another lesson. Okay, see you in the next lesson.